Hello everyone, welcome to this presentation called Introduction to the Finite Difference Method in Computational Fluid Dynamics. My name is Hugo, and in the previous videos in my channel, we solved the Navier-Stokes equations for two flow cases. One of them was the simple shear flow, and the second one was the shear flow with pressure gradient. So in those problems, we obtained an analytical solution for the velocity profile. So if you have not watched those videos, I recommend you to do it, because we will be using the solutions from those problems in this video. So my goal in this video is to give a brief introduction to what is the finite difference method. So I will start by describing what is it. I also want to give a brief explanation of the most common finite difference schemes, which are the forward difference, the backward difference, and central differences. I also want to explain how can we approximate derivatives using Taylor series. We will also be doing some quick computations of some first and second derivatives of some functions using these finite differences. And then at the end, my goal is to illustrate how do we use the finite difference method to solve problems in CFD. In this case, we will be solving very simple flows, which are the shear flow and the shear flow with pressure gradient. So let's start with this presentation. So calculation of a derivative. So from your calculus lectures, you probably remember that the derivative of a function f can be defined as the limit when h tends to 0 of this difference, which is the f. We evaluate f at the point x plus this h minus the function evaluated at x divided by h. So a derivative can be seen as the rate of change of the function f in a given interval, and the concept of derivative has important applications in physics, in chemistry, and of course in fluid mechanics, because the derivatives appear in the most important equations used in computational fluid dynamics, for instance, the mass, momentum, and conservation equations. So that's why it is important to study them, to understand them. So you also probably remember that if we have a function that is constant, the derivative is going to be equal to 0. If we have a function that is equal to x, the derivative is going to be a constant. If we have a function that is equal to the exponential of x, the derivative is the exponential itself. So those formulas that we learned in our classes, in our lectures, are exact solutions, are exact equations that were obtained by applying this concept, this definition of derivative. So those are exact solutions to compute the derivative of a function. However, sometimes we might have a very complicated and complex function, and it is almost impossible to obtain a derivative. So instead of doing the algebra to obtain the exact solution for the derivative, we can estimate the value of that derivative using approximations. So for instance, let's say we want to estimate the derivative of a function f in a point A. So that derivative can be approximated as follows, where x, we will evaluate the derivative in the point A. So that computation is carried out as follows. So we need to obtain the limit of the function evaluated at x minus the function evaluated at a, at the point A, divided by this difference. So we apply the limit when x tends to a. So this function, this limit, can be seen as a slope of the tangent line at the point A of the function f. So the finite difference term is used to approximate derivatives or slopes. So this is what I was talking about. So finite difference is the method that we use to obtain an approximation of the derivatives of some functions. So in finite difference methods, we will use values of the function f in the vicinity of the point x equal to a to obtain an approximation of the derivative. And also there are plenty of finite difference methods that are used to calculate derivatives. And in the majority of these methods, we will need at least 2 points near x equal to a. So I'm going to show you some examples of these finite difference schemes. So the first one is called the forward difference. So this method is used to estimate the slope of the function fx at the point xj using the line that connects these 2 points. So let me show this sketch. So we have the function f, which is defined, is illustrated here in red line. So here I introduce 3 points. So at this point is the value. This point corresponds to the value x j minus 1. So this point here is corresponds to x j, and this point x j plus 1. So if we evaluate f, this is the value of f at x j, and this is the value of f at x j plus 1. So we want to estimate the value of the derivative using finite differences. So we need 2 points. So we need these 2 points. We will estimate this difference here, which is just this value of f minus this value of f over this difference between the x's. So here in black, I represent the line that connects these 2 points. So the point xj and the point xj plus 1. So, and yeah, this blue line represents the exact value of the derivative of f. So yeah, I just wanted to illustrate that f, this black line is an approximation of the derivative. We are here calculating this line with these 2 points in order to estimate the value of the derivative at this point using the forward difference. Now let's talk about the backward difference. So the backward difference is very similar to the forward difference, but instead of using this point to evaluate the derivative, we will be using the point behind xj, which is where we have xj minus 1. So here I want to estimate the derivative of f at this point. So I will be using this value minus this value over this difference. So the black line is the line that connects these 2 points, the one evaluated at xj and the one evaluated at xj minus 1. So also the blue line represents the exact value of the derivative. But here the black one is the line that connects these 2 points. And now in the central difference, we will now use these 2 points, the one behind and the one here, in order to estimate the value of the derivative f at this point. So as you can see from the equation 5, so we need this difference, which is the one at the top. So f evaluated at xj plus 1 minus f evaluated at the point xj minus 1, and then divided by this whole difference, this whole interval from here to here. So how exactly do we get these equations that I show here? So we use a Taylor series to obtain approximation of the derivatives of the function f. So also you remember probably from your calculus or differential equations lectures. So the Taylor series of f near the point A can be estimated as follows. So this is a series. So yeah, I'm not going to explain the full equation. I'm just illustrating here the equation that you all recognize. So now let's say I want to use this Taylor series. I want to estimate the value of f at this point at x is equal to x j plus 1. So I just substitute this point here, and then I obtain this expression. So so you see that I need in order to estimate this value, I need the value of the function evaluated at xj. I also need to estimate the first derivative and evaluate it at the point xj, and so on. And so I'm just considering second derivatives, but you can go on. You can obtain the third derivative, the fourth one, and so on. So now let me define this h, which is just simply this difference that can be seen here. And then from this equation, I want to isolate this first derivative that is here. And then you do the algebra, you will end up with this equation. So you probably recognize this equation, which is the forward difference equation, which is here. So in order to evaluate the derivative at this point xj, I need to compute this equation. And then I include some this term, which is the OH, which represents the higher order terms. So that means that here are those terms, the second and the third derivative, that are going to depend on h. So these terms describe the accuracy of our finite difference equation. So again, let's say we want to estimate the derivative of this function. So if we want to use this equation, we are some sort of ignoring this term. So we are introducing an error into our computation. So for instance, if h is small, is 0.1, this term that involves the third derivative of the function f, so this term is going to be very close to 0, but this term is going to be non-zero. So that's why we say that this whole equation is of order h, because by ignoring this term that is non-zero, we will get a not so accurate value of our derivative. So that's why we say that these terms describe the accuracy of our method. In some schemes, in some finite difference schemes, we might have some accuracy where h is going to depend on this index p. So in p indicate the order of magnitude of the approximation. In the majority of the cases, the higher the value of p, the more accurate the solution will be. So I will show some examples about this in a few minutes. So now let's estimate the backward difference. So now instead of now we will evaluate the Taylor series near this point xj at xj minus 1. So if we do something similar, so we substitute here xj minus 1, and then we isolate the first derivative, we end up with this equation, which is the backward difference that I show here, which is also, it happened to be also of order h. So we will be ignoring, by calculating the derivative using only these terms, we will be ignoring these terms that are here. So it will not be so accurate if we use middle large values of h. So in order to estimate a good solution, in order to get a good accurate value of the derivative of f at this point, we need to use very small values of h so that these terms can be zero or very small at least. So now let's assume symmetry. That means that h is going to be equal to this difference, and this difference is going to be equal to this difference. So that means that this difference is the same one as the one here. And then we obtain the Taylor series near a equal to xj for these 2 points. And then we have a Taylor series equation for this f evaluated at x j plus 1. And then we have another Taylor series for f evaluated at x j minus 1. And then you can see that these equations look very similar. So I'm only consider the up to the third derivative, and the only differences appear in the first derivative, where we have a positive sign here and a negative one here, and the same happens for the third derivative. So now let's subtract these both formulas, and then we will isolate this term, and then if you do the algebra, you will obtain this equation, which happens to be the central difference. So something important to mention is that this equation is of order 8 to the 2. So that means that it doesn't matter if we have some slightly large values of h. This approximation is already good. So this equation will be a good approximation to the derivative, because the terms of order 8 to the 2 only involve the third derivative, and this third derivative depends on h to the 2. So if we have, for instance, a value of h equal to 0.1, this term is already going to be small. So yeah. Yeah, as you can see, the second derivative is going to cancel out for this case, so that's why we are not including a term that involves the second derivative. So this equation is true if the function f has a third derivative. So what happens if we want to estimate approximations of derivatives of higher order, for instance, the second derivative of f? So we can obtain also equations, schemes, the finite difference schemes for these higher order derivatives in a similar way as shown here. So now let's put an example. So we want to obtain the Taylor series near a equal to xj for these 2 points. So once again, we will have 2 equations, one for f evaluated at this point, xj plus 1, and another one for f evaluated at xj minus 1. And now I want to include the 4 derivative. And yeah, you can notice again that there are some similarities, but also some differences. The first derivative will have different signs, and the same happens for the third derivative. So now if you sum these 2 equations and then isolate now for the second derivative, which is this term, you will obtain a second order central difference approximation, and it will adopt this form. So compared to these equations that I showed here before for the backward, central, and forward difference, where we only use 2 points to evaluate the first derivative, 2 points. For the second derivative, we need 3 points. We need the value of f at this point, the value of f at this point, and the value of f at this point. So to estimate the second derivative of f. And this finite difference scheme is also ordered of h to the 2, and the only term that we are ignoring by computing the second derivative this way depends on the fourth derivative, which also depends on h to the 2. And once again, if we use relatively small or relatively or not so large values of h, this term is already going to be small. So this computation is already a good approximation to the second derivative. So now let's practice these equations. Let's put in practice these equations for using some examples. So now let's say we have this function which is the sine of x, and now I want to obtain the first derivative of this function evaluated at x equal to 1. So if you do the algebra, the derivative of x of this function is cosine, and then if you evaluate the cosine at 1, you will obtain this value. So now I want to use the three difference methods that I showed before, the forward, the backward, and central difference, to estimate the first derivative of f. And then I use different values of h, which are reported here, and then I estimate I obtain an approximation of f using these methods. For this table, I use the forward difference, and then I compute the derivative of f for these different values of h, and then the error is calculated as just the difference between the approximation minus the real value, the exact value of the derivative, divided by the real value multiplied by 100. So that's how I obtain the error. And this, as I mentioned before, forward difference is of order h. So if, for instance, if I use a not so small value of h, you can see that the error is slightly high. So this is not really a good approximation of the derivative. So I need to decrease h, and you can start to notice that this approximation is much better, but it's still far from the real value of the derivative, because now the error is 0.78. And now if I decrease h, I'm still getting relatively good values of the approximation to the solution. So now the error is going to be 0.077, and I will start to observe more accurate values when I use smaller values of h, for instance, for this case, which as you can see, the approximation is almost close to the real solution. Now the error is high, and if you decrease h even more, you will notice that we are getting even closer to the solution. For the backward difference, also I do the same. If I use a not so small value of h, I'm getting also not so good estimate of the derivative, because the error is still high, but is smaller compared to the error observed for the forward difference. And then if I start to decrease h, I'm getting closer to the real solution. And now what is happening for the central difference? So central difference is of order h to the 2. And you can see that here, this value of h is not so small, but we are already getting a good approximation of the derivative, because the error is much smaller compared to the errors observed for the backward and the forward differences. And I'm getting even more accurate values as I decrease h, as you can see in the errors. So that's why central difference is of order h to the 2. This scheme is good, it's accurate and this is the most used scheme to evaluate first order derivatives. And now let's compute the second derivatives using the central difference scheme that I show here for this function. Now the function is going to be equal to the exponential of x to the 2, and if you do the algebra, you can obtain the second derivative of this function, which is going to take this form. And now I want to estimate the value of the second derivative of f of this function at x equal to 1. And also you can estimate this value by hand or using your calculator. And yeah, this is the real exact value of the second derivative. And now I'm going to do something similar as shown before. So I'm going to evaluate here is the second derivative of this function using different values of h. And yeah, you can notice that the central difference is also of order h to the 2, because I'm already getting good estimates of the second derivative, even if h is not that small. And if I decrease even further h, I'm getting basically the same value compared to the real solution. And this is illustrated in the errors here. So now, once that we introduce these finite difference schemes, I want to apply those methods to solve two simple flow problems, which were solved in my previous videos. So the first one is simple shear flow for a Newtonian fluid, where we have a Newtonian fluid contained between these two parallel plates. The bottom plate is fixed. That means that the velocity at this point is going to be equal to 0. The top plate is moving in x direction, in here towards this direction, with a velocity uv. These two plates are separated by a distance h. And we will assume that the viscosity of the fluid and the density are going to be constant. And also we assume isothermal steady state. So that means that the temperature is going to be constant, and we do not care about the temporal terms. We only care about the solution once that steady state is reached, when the system no longer depends on time. We also want to solve the shear flow with pressure gradient, which is just simple shear flow. This flow is very similar to this case, but we will be adding an additional source of movement, which is we will be applying a constant pressure gradient. So that means that there is some sort of mechanical device here, for instance a pump, that is going to push the fluid in x direction. So from my previous videos, we solved the Navier-Stokes equations for these two flows. And for simple shear flow, which is this flow, the one here, we obtain this analytical solution for the velocity profile, which depends on the velocity at the top plate. It also depends on the distance between the two plates, and it depends on the y coordinate, because the velocity depends on this direction. And also for the shear flow with pressure gradient case, which is the one here, we obtain a slightly more complex equation, which has two contributions, the one due to the movement of the top plate, and the one due to the additional force that is included into this flow, which is due to the action of a mechanical device that is pushing the fluid in x direction. So now, using the finite difference method, we wish to find a numerical solution for the velocity field in both flows. And to achieve this, we have to solve the momentum conservation equation only for the x component. Also, for my previous videos, this is the equation, the second order differential equation that we solve to obtain these two velocity profiles. But I want to illustrate the finite difference method into these two cases. So this equation involves an f for where f is a source term So when f is equal to 0, we have the simple shear flow case, which is the one here, and when f is equal to the pressure gradient, we have the case here. So remember, we want to solve this equation using the finite difference schemes that we applied before. So now mesh for the finite difference method. So a mesh is a subdivision of a continuous geometric space into smaller cells. So that means that in order to apply the finite difference schemes, we have to split our domain, decompose our domain, which is this channel, which has a height of equal to h. So our domain is composed y, the coordinate y is within the interval 0 and h, and we have to decompose these two domains into smaller cells that will have a size equal to h, which is just going to be defined as the height, total height, divided by n, where n is the number of specified cells. So let me explain this. So here we have our domain. So here we have the bottom plate, we have the top plate. So h is the distance between these two plates. So I want to split this channel into smaller cells, and each of these cells will have this size, which is equal to h, and h is going to depend on h is going to be calculated as this height divided by n, and then I want to specify I want to solve this equation in 6 cells. So I split this domain in 6 cells. So you can count them. So we have 1, 2, 3, 4, 5, 6. And then in the finite difference method, I want to estimate the velocity values at each of these cells, so which are represented in these blue points. So discretization of the equations using finite difference. So by discretization, I mean that the purpose of any discretization technique is to transform one or more partial differential equations into a corresponding system of algebraic equations. And the solution of this system will produce a set of values which correspond to the solution of the original equation at some predetermined locations in space and time. So that means we will apply some sort of mathematical technique to express these derivatives into algebraic equations. So for instance, as I said before, we want to apply the finite difference method to solve this differential equation. So you remember that we derived an equation to estimate the second derivative of the function f. So we will be applying this equation, which we show that this equation is a good approximation to estimate the second derivative of a function. So we will be using this equation here to estimate the second derivative. So that means that we need 3 points to evaluate the second derivative. So let's say we want to compute the second derivative at cell 1. So cell 1 is here. So that means that we need 3 points. We need u2, which is the velocity value in cell 2. We also need u1, which is here, and then we need u0, which is here. So at cell 1, at this cell, we need the value of the velocity at the cell at the bottom, and then we also need the velocity value at the cell above. So if we substitute this approximation of the second derivative into this equation, we end up with something like this. So we have the viscosity multiplied by our approximation of the second derivative plus the source term, and this is the momentum balance equation in cell 1 in this cell. And now you can notice that here at the top we are at the top plate. So that means that we already know the velocity value of u0, which is equal to ub, which is the value of our boundary condition. So this is what I meant. And now if I rearrange this equation, I'm sorry, I obtain this equation. Now I already substitute u0, which is equal to ub. And now you can do the algebra, and then you will end up with the same equation that is shown here, this equation 23. And now I want to estimate the second derivative at each of these cells. So let's do some quick calculations. For instance, for cell 2, you notice that here we need the value of the velocity at cell 1. Here we need u2 and we need u3. And then you rearrange the equations, and then you will end up with something like this. So also you apply this definition of the second derivative for cell 3. Then you will notice that you will need u2, u3, and u4. And then if you rearrange these equations, you will end up with something like this. And then you carry on up to cell 5, and then you obtain this equation. So you do the momentum balance equation for each of the cells. And then u6 is 0, because u6 is defined here at the bottom plate, and we know from our boundary condition that the velocity at the bottom plate is going to be equal to 0. So uc is equal to 0. And also we don't need an equation for this cell, because that will imply that we need u7. So u7 is already outside the domain, so we don't need an equation for a momentum balance equation for cell 6. And now you can notice that I arranged these equations because you can notice that we can assemble this system of equations. We have variables. All these terms are variables, and the terms to the right hand side are constants, because f involves constants. F is equal to, remember, is equal to the source term. Pressure gradient is constant. F is equal to 0 for simple shear flow. H is constant because it's the distance of the cells, and then mu is the viscosity. So all these terms in the right hand side are constants. So we can arrange these equations into a matrix system, which will adopt this form, which is a linear system. A is a matrix of coefficients, B is a vector of constants, and then U is the vector of variables, the vector of unknowns, whose solution will give us the velocity field we are looking for. So yeah, this is the matrix linear system we obtain from applying the finite difference method, where capital F is equal to these terms. So these kind of matrix systems are very common in computational fluid dynamics. So these systems are known as sparse matrices, because the majority of the elements are 0, which are the ones that are outside the diagonal, and the diagonal elements are non-zero. So this is a very simple metric system, but in reality, when you are solving an industrial flow case, an industrial flow problem, or for instance, you are solving a fluid mechanics problem applied into a chemical reactor, or the flow of a pipe, a very long pipe, you will have a matrix system of, let's say, 1 million components or more than 1 million components of your matrix. So these systems are very expensive to calculate because we need to find the solution of 1 million variables or more. It depends on your problem or the complexity of your problem. So CFD, any CFD software will solve this matrix linear system for you, so don't worry about it. So the CFD software is going to apply those numerical techniques used to solve these matrix linear systems, for instance, Gauss-Jordan. There are more complex ones, but I just wanted to show you so that this is the kind of systems we encounter in CFD. So now let's solve this linear system for the simple-shear-flow. So remember that for simple-shear-flow, f is going to be equal to 0. So now let's put some values to this constant. So we have our channel height, which is going to be equal to 1 meter. Then h, I specified 6 cells. So the cell size is equal to 1 over 6 meters. Then I'm specifying a value of velocity at the top plate equal to 1 meters per second, and then the velocity at the bottom plate is equal to 0. The viscosity of the fluid for practical purposes, it will adopt this value, 1 over 36. And then, yeah, we will solve this matrix linear system. We substitute these values I specified here into here, and then you solve. You can use any method, the matrix linear method, in order to find this vector. And then the solution for this system is this one. So we have this vector solution for the velocity profile, which has units of meters per second. And then if we compare our numerical solution, here, this one, with the analytical equation for the velocity field, which is this one, remember the ones that I show here for the simple-shear-flow. This is the analytical solution for the velocity profile. And then we compare these two solutions, and the red points represent these values. So here I introduce the boundary condition. When at y equal to 0, the velocity is going to be equal to 0. And when y is equal to h and h is equal to 1, I introduce the velocity value at the top plate. So these points in the middle corresponds to these values obtained from the matrix linear system, and the straight black line is the analytical solution. So you can see that the finite difference method gives us a good solution to this equation. Now let's solve the matrix linear system, but for the shear flow with pressure gradient. So we use the same constant values of height, velocity at the top plate, viscosity, but now we introduce a source term, which is the pressure gradient, which will adopt this value. So pressure gradient has units of pascals per meter, and then we substitute these values into here, and then we solve the matrix linear system, and then we obtain this vector field, which has units of meters per second, and then we will compare this solution with the one obtained from solving the Navier-Stokes equations. And yeah, this is the comparison. So the red points represent the solution here, and this line, this curve, is the solution from the analytical solution. So yeah, so this is how we solve. This is how we applied finite differences to solve fluid mechanics problems. So just to conclude, finite difference is the easiest method to solve fluid mechanics problems, because we just need to evaluate these derivatives using points, using values of the velocity at different points in the mesh. However, the problem with finite differences is that they only apply, or in the majority of the cases, they apply to very simple geometries. So for instance, if we have a more complex geometry, for instance, an irregular mesh, we might have, for instance, a plane or a car, a pipe composed of different elements. So finite difference becomes really complicated to apply. So in these cases, we need to look for different methods. And one of them is the finite volume method, which is actually the most popular numerical method used in computational fluid dynamics. So I will be talking about that method in the next video. So I just want to thank you for being here. If you have any questions, suggestions, let me know in the comments. So I appreciate that you are being here, you are watching this video.